Hello and welcome back. If you are new to this channel, consider liking the video and subscribing to the channel. Today, we are going to be looking at a few examples. We are going to solve the system exactly, and we are going to draw the face portraits. And these are a list of questions you're going to be doing. I will be doing the first one. I will also be doing question 2A and question 3A. The rest I'll leave for you to practice. Without much delay, we will take a look at the first example. I'm going to write down our system. So solution. Example 1. We are going to represent our matrix by B. And our values for the matrix are, we have 2, 2, 2, 0. So 2, 2, 2, 0. Since this is 2 by 2, we find the trace and the determinant. The trace is just by summing the values on the diagonal. So we have 2 plus 0, which is 2. We find the determinant, 2 times 0 minus 2 times 2, give us minus 4, which is less than 0. So the system is a saddle at the origin. Then we find our eigenvalues. Tau squared minus 4 delta divided by 3. So we input our values, which are 2 plus or minus square root of 2 squared is 4 minus 4 times minus 4, all divided by 2. So next, we will have our lambda to be equal to 2 plus or minus square root of, we have 4 plus 16, all divided by 2. So our lambda will be equal to 1 plus or minus, this will give us 2 root 5 divided by 2. Therefore, our lambda will be equal to 1 plus or minus square root of 5. We have our first lambda 1 to be equal to 1 minus root 5. And we have our lambda 2 to be equal to 1 plus root 5. So we see that this is less than 0 and this is greater than 0. We find our eigenvectors using B minus lambda I, V equals 0. So our first eigenvalue, you're going to have B minus lambda 1 I times V1 for 0. B is given by 2, 2, 2, 0. Minus lambda I is given by 1 minus root 5, our first lambda, 0, 0, 1 minus root 5. Multiplied by x and y, give us our 0, 0. Okay, next we simplify. We have 1 plus root 5. We have 2 here. We have 2 here. We have minus 1 plus root 5. X, y to be equal to 0, 0. We use the first line. So we have 1 plus root 5 multiplying x plus 2y, which is equal to 0. We have 1 plus root 5 x, which is equal to minus 2y. So in the end, we have y divided by x to be equal to minus 1 plus root 5, all divided by 2. So we have our V1 to be equal to, let's conclude first. We have if y is equal to minus into bracket 1 plus root 5, then x will be equal to 2. So x is 2 and y is minus into bracket 1 plus square root of 5. Now let us write an equation of a line. So we have written the equation of a line from this place. So we have y is equal to minus 1 over 2x 1 plus root 5. We will come back for this later. So we find the next eigenvector. So we have b minus lambda 2I v2, which is equal to the 0 vector. So we have 2, 2, 2, 0 minus 1 plus root 5, 0, 0, 1 plus root 5. Multiplying our x and y, giving us 0, 0. Now we simplify. We have 1 minus root 5, 2, 2. We have minus 1 minus root 5. Multiplying x and y, giving us 0, 0. Next, we use the first line, 1 minus square root of 5, multiplying x plus 2 times y, which is equal to 0. So we have 1 minus root 5 multiplying x, which is equal to minus 2y, and y divided by x is given by minus to bracket 1 minus square root of 5, all divided by 2. So if y is equal to minus 1 minus square root of 5, then our x will be equal to 2. So we found our v2 is equal to 2 minus 1 minus square root of 5, and we write our equation of a line. We have y equals minus 1 over 2 into bracket. We have 1 minus square root of 5. Okay, so we also highlight this. We'll come for it later. Next, we write our p, which is made up of v1 and v2. So our p is equal to 2. We have minus 1 plus square root of 5, and 2 minus into brackets 1 minus square root of 5. P inverse is given by 1 over the determinant of P multiplied by the adjoint of P. So we have minus into brackets 1 minus square root of 5. We have minus 2 here. And we have 1 plus square root of 5. We have 2 here. So we interchanged the diagonal and we negated the other diagonal. Okay, so the determinant of P is given by, we have 2 times minus 1 plus root 5 minus 2 times minus 1 minus root 5. So we go ahead and find, we have minus 2 plus 2 root 5, and you have plus 2 plus 2 root 5. So the determinant of P is given by, this cancels, and we are left with 2 root 5 plus 2 root 5, giving us 4 root 5. Remember, you're going to use 1 over 4 root 5. So we simplify by root 5 divided by 4 by 5, which is equal to root 5 over 20. So our P inverse is given by root 5 over 20, multiplying minus into bracket 1 minus root 5. We have minus 2 here. We have 2. We have 1 plus root 5. So these are P inverse. Now we recall that our solution is given by x of t is equal to e raised to the power the matrix given by b t x naught, which is simplified to be p e of t p inverse x naught. Our e of t is given by the exponential of the diagonal. So the first diagonal was negative. You have 1 minus root 5 all multiplied by t. You have 0, 0, and e raised to the power 1 plus root of 5 times t. Now remember, these are your eigenvalues. So the negative eigenvalue and the positive eigenvalue. Next, we are going to substitute everything into the expression to write down our solution. So our x of t is given by p, which is given by 2 minus 1 plus root 5 and 2 minus 1 minus root 5. Now we multiply it by e of t, which we have here. So e to the power 1 minus root 5 multiplied by t, 0, 0, and e of 1, e raised to the power 1 plus square root of 5 t, all multiplied by your p inverse and your x naught. Remember, you're supposed to multiply everything using matrix multiplication. So when you are done with everything, you will get your value for x of t. We are also told to sketch the phase portrait. So we draw our x and y axis. So we have our x and y axis, and we are going to sketch our phase portrait. Now for our phase lines, it is best to use different colors to represent them so that it will be more visible. Now, the equation of a line that we circled earlier is what we're going to use. That's going to give us our phase lines that we will need to plot our solution. So we have the first equation of a line. We have minus half x, 1 plus root 5. So we need to plot y equals minus half x, 1 plus square root of 5, and y equals minus half of x, 1 minus square root of 5. So we need to plot these two equations of a line. Let's label them 1 and 2 respectively. So if x equals 1 for the first one, we'll have y to be equal to negative 1 plus the square root of 5, all divided by 2. Now, square root of 5 is approximately 2.2. So we have 3 minus 3.2 divided by 2, which is going to give us minus 1.6, I think. And for the second one, if x is equal to 1, our y will be equal to, again, we have minus 1 minus square root of 5 all divided by 2. And this is going to give us 0.6. We are going to use these 4 values to plot our phase lines. So we have x, when x equals 1, let's say 1 is for x here, y is negative 1.6. So 1.6, let's say it's over here. So minus 1.6. So assuming they'll meet at this point, and that line will pass through the origin. So we have this line. And the next one, we have y to be 0.6. So somewhere here, which will give us a point here. When that one also passes through the origin, this line is given by y equals minus 1 over 2 x 1 plus square root of 5. And this line is given by y equals minus 1 over 2 x 1 minus square root of 5. Now, this line is our negative eigenvalue. This line is for our negative eigenvalue. So, and this line is for our positive eigenvalue. So we have this. Since we have a saddle, we're going to follow the phase lines to draw our solution curve. We're going to use a different color. Now we can draw our solution curves by following our phase lines. So we have, start from here and curve here. Start from the top, curve here. We start from here, curve here. We start from here, the bottom here, and curve. And we represent, use our lines to indicate the direction. So we have this line, we have this line, we have this line, and we have this line. So these are the directions where our solution will pass. We are done with this question. We solved for the eigenvalues, we solved for the eigenvectors, we found our P matrix, we found our exponential matrix, and we also sketched our phase portrait. That's it for the first question. We're going to move on to the second question. So for question 2, we have, let us represent our matrix by A and write down our values. Alpha plus 1, beta, beta, and alpha minus 1. Now, there's no need to put in the values for alpha and beta right now. I'm going to show you the reason why. Now, to find our trace, we need to add the values on the diagonal. So we have alpha plus 1 plus alpha minus 1, which will give us alpha plus 1 plus alpha minus 1. This will cancel this, which will give us 2 alpha. And for our delta, we will have alpha plus 1, alpha minus 1, minus beta squared. So we're going to factorize this. We're going to have alpha squared minus 1 squared minus beta squared. So our delta is going to be alpha squared minus beta squared minus 1. With this, Now we have an expression for tau and delta. So we can use our lambda equals tau plus or minus the square root of tau squared minus 4 delta all divided by 2 to find our eigenvalues. So we're going to solve for A, and I'm going to leave the rest for you to practice. A is given by alpha equals minus 2, beta equals minus 1. Okay, so our tau will be equal to 2 times minus 2, which is equal to minus 4, and delta it will be equal to alpha squared, so we have minus 2 squared, minus beta squared, so minus 1 squared, minus 1. And this is going to give us 4 minus 1 minus 1, which is equal to 2, and which is greater than 0. So we can make a partial conclusion. So the system is a node at the origin. Now remember, this is a partial conclusion because you're not stating whether or not the system is a stable node or unstable node. So when we go ahead and find the eigenvalues, then we make the complete conclusion. So we have lambda to be equal to tau is given by minus 4 plus or minus the square root of tau squared, which is 16, minus 4 delta. Delta is 2, so 8 all divided by 2 is going to give us minus 2 plus or minus the square root of 8 divided by 2, which is minus 2 plus or minus root 2. The square root of 8 is 2 root 2, and we are dividing by 2. So lambda is equal to this value. So lambda 1, we take the negative side, we have minus 2 minus square root of 2, which is less than 0, and lambda 2 will be minus 2 plus the square root of 2, which is also less than 0. The square root of 2 is 1.4142 approximately. So minus 2 plus 1.4142 will give us a negative value. So now we can make the complete conclusion that the system is a stable node at the origin. So this is our complete conclusion. Next, we want to find our eigenvalues and eigenvectors. So our eigenvalues, we have lambda 1 to be equal to minus 2 minus square root of 2 is less than 0, and lambda 2 to be equal to minus 2 plus square root of 2. So A minus lambda 1i, V1, and we're going to have minus 2 plus 1. We have beta to be minus 1. We have minus 1. We have minus 2 minus 1. All this subtracted from minus 2 minus square root of 2, 0, 0, minus 2 minus square root of 2, multiplied by x and y is equal to 0, 0. So next, we have minus 1, minus 1, minus 1, minus 3, minus, we have here minus 2 minus root 2, 0, 0, minus 2 minus root 2. X and y is going to give us 0, 0. Minus 1 minus 2 is 1, plus square root of 2. And we have minus 1 minus 1 minus 3 minus 2 will give us minus 1, then plus square root of 2, multiplied by x and y, giving us 0, 0. Next, we take the first line. We have 1 plus square root of 2 more multiplied by x minus y, which is equal to 0. So we have y to be equal to 1 plus square root of 2x. Therefore, y divided by x is going to yield, we have 1 plus square root of 2 all over 1. So if y is equal to 1 plus the square root of 2, then our x will be equal to 1. So we found our v1, which is equal to 1 plus square root of 2. We're going to find our v2, so a minus lambda 2 I, v2, we have minus 1, minus 1, minus 1, minus 3, minus, we have minus 2 plus root 2, 0, 0, minus 2 plus root 2. All these multiplied by x, y, giving us 0, 0. Again, you're going to simplify. We have minus 1 minus 2. So you're going to have 1 plus root 2. And we're going to have minus 1, minus 3 minus 2. We're going to have minus 1 minus root of 2. This is supposed to be minus, multiplied by x and y, giving us 0, 0. So we have again, take the first line, 1 minus square root of 2, multiplying x minus y is equal to 0. So 1 minus square root of 2 multiplying x is equal to y. Y divided by x is going to give us 1 minus the square root of 2 all over 1. Again, if y is equal to 1 minus the square root of 2, then x will be equal to 1. So our v2 is equal to 1 and 1 minus the square root of 2. So our P matrix is given by 1, 1 plus square root of 2, and 1 minus square root of 2. We can go ahead and find our P inverse as 1 minus square root of 2 and 1 minus 1 and minus 1 plus square root of 2. Determinant of P is given by 1 minus square root of 2 times 1 minus 1 times 1 plus square root of 2, which this gives us 1 minus square root of 2 minus 1 minus square root of 2. This cancels, leaving us with minus 2 root 2. So 1 over minus 2 root 2, we're going to have minus root 2 all over 4. So our P inverse is given by minus root 2 over 4 multiplying, we have 1 minus root 2 minus 1 minus 1 plus root 2 and 1. So these are P inverse. So we found our eigenvalues, our eigenvectors, and our P inverse. Our E of t is given by the exponential of the first eigenvalue. So exponential of the first eigenvalue, which is minus 2 minus root 2 multiplied by t, you have 0, 0, and e raised to the power minus 2 plus root 2 t. So now we have everything we need. Remember, our solution is given by x of t, which is equal to e raised to the power a t x naught, which is given by p e of t p inverse x naught. So we have our x of t to be equal to, we have our p, which is given by 1 plus root 2, 1 minus root 2, or e of t, e raised to the power minus 2 minus root 2 times t, 0, 0, e raised to the power minus 2 plus root 2 times t, and our P inverse, which we just found. So our P inverse is given by root 2 over 4 minus root 2 over 4, sorry. And we have 1 minus root 2 minus 1, 1, and minus 1 plus root 2. So multiplied by x naught. So this is our solution. Our phase portrait. So we have our y and our x. Our equation of a line for the two values, we write it down here. We have y is equal to, we know that y is equal to 1 plus. So we have 1 plus square root of 2x and 1 minus square root of 2x. So if x is equal to 1, y will be 1 plus square root of 2. If x is equal to 1, y will be equal to 1 minus square root of 2. And this is approximately 2.4, and this is approximately negative 0.4. So we indicate x equals 1. Okay. And y equals 2.4. It's around here. Y equals negative 0.4. It's around here. And they are all passing through the origin. So since they are both negative, the eigenvalues are both negative, we have our directions pointing inward toward the origin. So we have this, 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 and this. Our eigenvalues, the lambda 1 to be smaller than lambda 2. Recall that the greater eigenvalue will have its solution curve to be parallel to our phase line at infinity. So we have, and while it's approaching, it bends towards the origin. So the same thing happens here. But this is going to be our direction. So you can have other solution curves. Because we want to represent them for all time, we can add the opposite side. So parallel, then toward the origin. Parallel, toward the origin. Parallel, toward the origin. Parallel, toward the origin. Okay. So this is our phase portrait for our system for all time. So time here belongs to the real line. Okay. This is it for this video. I'll see you in the next video and we will continue to solve more examples.